Not the water yet. We know water. Okay, the first one, the useful ones turn out to be, the most useful ones turn out to be metals reductors. So the column is going to be filled with metals. Okay, the first one, credit to this guy named Jones. So it's a reductor called column. So he came up with, okay, you fill the column with granular metal, zinc. Okay, so you want this to be granular to increase the surface area for reaction. Okay, but it cannot be too small. If it's too small, then you have back pressure, like nanoparticles. It's totally plugged that you need high pressure to pass through. So granular is sufficient. So this entire column functions as your half reaction, right? Your half reaction. And then your sample represents another half reaction. So as you pass through, then you have a redox reaction complete here, and then you come out as product, okay? So what it amounts to that, this half reaction combined, your E overall must be positive, right? So that is the theory behind. But then most people do not care of the theory. They only see whether it works or not. And there will be a table for you later on. So the granular zinc, and then on the zinc is coated with mercury. So mercury is not good. So this more people get away from using this column because of that reason. Now the reason for the mercury is to prevent acid reaction with the zinc. Okay, then zinc metal, so this is neutral solid, and will form hydrogen gas and dissolve the zinc, so reducing the efficiency of the column because of less zinc available. Okay, example here. So your sample contains Fe3 plus and Fe2 plus. Okay, so the 3 plus will get reduced according to this overall reaction. So you can prove this by doing the E overall calculation. The E naught overall must be positive because it works. Okay, so as an exercise at home, do this. Ignore the mercury, just zinc neutral to zinc 2 plus. Then the E overall must be positive. So this is your reaction product. So this will combine with whatever the Fe2 plus already there. So you have the total for titration. So your analyte is in a reduced form. Okay, you will need to use the oxidizing agent to titrate against this. Another example is for the titanium. The 4 plus pass through the column, then it becomes 3 plus. So your zinc, this will simultaneously in your solution. Okay, but this is an oxidized form, and this is a reduced form. So if you use oxidizing agent to titrate this mixture, then this oxidizing agent will oxidize that. So there's a reaction, but will not oxidize this anymore because it's already oxidized. So this will not interfere with your titration. However, you realize, the zinc is being removed progressively. So that means you need to refill the column after some use, prolonged use. Any question?
The zinc amalgam, that's just zinc mercury, right?
Yeah.
Okay.
Yeah, but active chemical is the same. Okay. Now Warden, Warden is a famous name. We try to look him up in like this puzzle. My son has. Where's Warden? Make the puzzle how to find it. It's a lot of fun. Okay, so he came up with this column filled with metal. So the structure of the metal is spongy metal. So for the purpose of, again, is facilitate solution to pass through and reaction. So spongy granular silver metal, so it's silver. Nowadays, silver is expensive, approaching $40 an ounce. So to fill this with silver is pretty expensive. But it works real well. Okay, so this is a reaction. For example, you're going to reduce the 3+, go through the column, you will need to have HCl in it. So we will see why, what's the purpose for HCl. It turns out that you need chloride, Cl-, for this reaction to work right. Okay, so this is your overall product. Okay, so you go to get a precipitate of that, then perhaps you can collect that and then regenerate the silver because of the cost. Silver chloride in the mixture as precipitate. Then this is your analyte for titration. Okay, simultaneously, then you add that, it's still acidic solution. Okay, let's look at what happened because the column reaction appears to be just between the cation and silver. Then why not just use silver alone without that in the solution? So that would be the if without the chloride, then you're going to have these two half reactions, right? So your purpose is 3+ to 2+, so this position will stay. That is a reduction potential. And this is also reduction potential. Then for oxidation, you will switch the top one. So once that is switched, then you would match for this desirable reaction, right? But then notice once you switch that, then this becomes a minus 0.8. Minus 0.8 plus 0.7, then you end up with a minus. So the reaction will not go, right? Okay? So now with chloride, then your reaction, half reaction is different. The half reaction turns out to be this one. With chloride is this one. Okay? So there's a reduction half reaction. So if you're going to switch this as oxidation because you have decided this must be reduction, right? So you cannot change this this position. So on purpose, this position is fixed. Then the other one must switch. So this is what you do. You switch this one. Then once this is switched, then you get the overall reaction just like that one. And then when this is switched, then this is minus, and this is plus, this is minus. So the two combined will end up with a plus. So the reaction goes. Okay, so that explains the reason for having chloride. Okay, any question? Okay, so I mentioned previously when you have a metal ion solution, then pour into a column, so this becomes your overall reaction, right? So as long as your E overall is positive, then you're going to get the the reaction product. So this will be the reaction product, and this will be your analyzed to be reduced through the column, okay? So between here, the two will be your complete reaction. Complete reaction, the E overall positive, then it will go, okay? So these are the products for the positive E overall. These are the products. Okay, so that is the theory you need to know. So I stress the theory behind, and I'm not asking you to memorize, what pour into the Jones column, then what comes out of the Jones column. I will not ask you to memorize anything like that. Rather, keep that in mind. The E overall is equal to positive, then you get the products. So I could give you an ion, any cation. Then I give you a table. Then I said that you pass that solution into this column. Then what product do you get, or is it possible? Okay. So do not memorize this. But here is just to show the outcome. Okay, the outcome here. So the chromium 3 plus pour into the same column, the Jones column, then you get chromium 2 plus. 2 plus is further reduced. Okay, nothing will happen with the Warden column. So not everything works, the way you want it to be. So not work for this particular column. Okay, so and so forth, and this one is interesting. So the 4 plus go into the Jones column, get reduced. And then if you go into the Warden's column, then you want to reduce me, I oxidize you, So you're like, this is tougher guys. So you do the opposite. You come into my house, right? I push you back. So oxidize instead of reduce, even though it's called a reductor, okay? But because of when you combine two half reactions, the opposite, go to 5 plus will be positive, okay? So keep that in mind for some particular. Okay, here is another particular. This example, you get 2 oxidizing state, 2 states. Okay, so if that's for a purpose, then that's good. Otherwise, then you use a different column, then you get just 1 oxidation number. Okay, so after the treatment, the pre-treatment, then now you analyze. So this becomes your secondary analyze to titrate forward. Okay, so they are all in a reduced form. So to do titration, you will need oxidizing titrant, okay? Oxidizing agent. Any question here? Okay, so
if I was gonna Google different kinds of columns, what would you put it in under? Like just different kinds of.
the keywords would be like the keywords I use.
Yeah.
For redox titration, plus encode, and then plus reductor columns,
Okay.
and then plus metals, so on and so forth.